Okay, so GPS tracking with Python. So my history is a bit complicated. I've worked on a whole bunch of different odd things. The most recent big project that I've done is I did an absurdly huge video course on Python for O'Reilly, which I'm speaking about again on Sunday. And besides that, I don't want to go into too much. I've started an education platform called codeemoji.com, and my blog is pythonomicon.com. I spoke in last year's education miniconf, and Carrie Ann Philbin, the director of the Raspberry Pi Foundation, was in the audience, and she blogged that I was a very nervous developer. So if anyone blogs, please don't say I'm nervous. Okay, so about this talk, it's really about approaching GPS tracking from the perspective of an application developer. So if you're not a hardware guy or you're not someone who's building the devices or anything like that, but you're really wanting to write a platform.
Is that on? Right. Yeah, it's on. It's on. Yep. Yep.
Is it just not catching me?
It's moved. Sorry, mate. Apologies. Try that.
Testing. Better. Okay, so the application lifecycle from the point of view of an application developer. So you're receiving data that is coming in from devices. You have to receive it, process it, and store it. So the menu for the talk is pretty simple. So we're going to look at the source of the data, where it comes from. And I'm going to focus just really on OBD vehicle devices, these things that you plug into your car. And I'll show you what that looks like shortly. The destination, where the data actually gets sent to, which is the server that you're responsible for writing. And then how you do a little bit of message handling. There's not a lot of time to go into detail, so I'm really going to give a high-level overview of each of these sections. I'm moving quickly because I think I have too many slides, so if I begin to accelerate at the end, that's what's going on. So we'll start at the data source, and this was a really hard picture to find because you don't find many pictures that can clearly communicate cars transmitting data. But if we're talking about OBD devices, that's really what happens. The OBD device plugs into the car and it transmits a signal, usually via GPRS, once you provision the device over the cellular network. That's the kind of thing that I'm talking about. So this is an 8-track model, but there are others that look incredibly similar. They're really nothing much to look at. They're little black boxes, and they literally plug into your car. So if your car has been made within the last 10 to 15 years, you almost definitely already have one of these waiting for something to plug into it there. This is an American vehicle, so the steering wheel's on the wrong side, but it would be in a similar place on the other side. If you have never checked before, check in your car and you'll see one of those ports. So now we're starting to get to more detail about these devices. There are a huge number of vendors, and they all observe the spec for the OBD port itself. But what we'll get to is that everything else about the process, they have come up with their own implementations of everything. And when you're building a platform that has to abstract away the differences between different devices, that's really quite a lot of work. And you'll see what I mean in the next few slides. Okay, so one thing you can do as well is you can receive data from mobile apps. You don't have to write your own. There are a couple of apps that will already transmit data to a server of your choice, and they publish some protocol documentation about what the payload looks like. And typically, you'll write a TCP server because devices, so this device submits HTTP messages, but for the OBD devices, they usually make TCP connections. This app in particular is quite well written and gives you a lot of information about your cell phone. And it will cache data if it cannot transmit and then batch it up later. So if you want to play around with writing servers to receive GPS data, that's a good app to get as a starting point. And it runs on both Android and iOS. So that's the hardware part finished. The other talks were very hardware-centric, which is what I expected. So I'm rather going to focus more on what you do with the data. And that's supposed to be a picture of a server. I don't know if that's obvious or not. So as James explained earlier, with Internet of Things type situations, you're really dealing with a huge amount of clients, different connections. And so you really have to do event loop type programming to manage all of these concurrent connections. That's the metaphor here. So the fish are the devices, and you have to write the server. So it's a high concurrency situation. So with the OBD devices, the vast majority of them do TCP connections, and really long-lived TCP connections. The keep alive period is around 4 hours, to give you an idea of what we're talking about. And many of the devices they're able to communicate in either TCP or UDP, and you can determine how they do that by provisioning the device with a particular configuration. Very few devices, but there are some of them, they do UDP only, so that they will not do TCP connections. And as I mentioned before, they use event loops. You have to use event loops because if you have tens of thousands of devices connected to your servers, you'll run into the 10K problem. You simply run out of enough memory to produce the threads necessary to serve the clients. So if you start doing this kind of work, you'll see that there are already a bunch of pre-existing frameworks for doing event loop-based servers in Python. In my particular case, before I started working on this project, Tornado had already been selected in the stack, which is really good because Tornado is awesome. It has an extremely simple API, and you can get started very quickly. There's just one problem. Tornado doesn't include datagram support in the stack. And there are some devices which you only realize after you've implemented 15 protocols that Tornado doesn't do UDP by default. So what you do is you check out py, and there are not that many options, and then you check GitHub, and there are a couple, but the code looks shaky, and there are comments towards the bottom of the page that says, this is broken, don't use it. So what I did to get around that in a very short turnaround time was I wrote a bridge that bridges UDP to TCP so that I could treat the implementation of the device protocol for this particular device in exactly the same way as the others. So its protocol implementation is also done with Tornado, but there's a UDP bridge sitting in front of it, which is probably not the right thing to do, but I could get it done in a day. And the reason for that is because async IO already provides UDP and TCP with exactly the same API. One thing to point out is that there is a new event loop, really, called UV loop, which is a third-party library that matches the same API as async IO. UV loop is implemented in Python, and its performance in single-threaded mode is exactly the same as Go. It's really, really incredible. So if I were to start such a platform-type project again, I definitely would begin with async IO and use UV loop. Yeah, so this is a good point. This is what you will begin to see when you start benchmarking your servers. Concurrency is actually a CPU-bound process, which is really interesting because what you're talking about all the time is networking. And we get used to the idea that anytime you're working with networking stuff, CPU doesn't really matter. If you're within 10, 20 times of a compiled language, it doesn't really matter because you're IO bound and you're waiting on event processing. The thing about concurrency is once you begin adding multiple clients, you actually do need to shard out that CPU time to many different clients. So it actually does begin to matter, and you definitely see that when you start comparing the different tools. That's why UV loop is so incredible, because it actually gives you all this headroom, because all of the event processing is based on libuv. So the amount of concurrency you can do with UV loop as opposed to just plain async IO or Tornado or Twisted or any of the other frameworks is much, much better. Okay, so message handling. As I mentioned before, each of the different device vendors, almost to a man, has implemented the device protocol in a different way, and in a completely different way. Like they aren't even matching characteristics, how they do byte packing and all of those things. So it almost feels like you have to start from scratch. Every single time a new vendor comes on, you have to read their protocol documentation, see how they differ from everyone else, and see if you can try and abstract some commonality from what you've done before for previous protocols. And there usually isn't much, and that's really incredible to me, because the data that they provide largely is almost exactly the same. I find that's really incredible. And it seems to come up quite frequently in hardware-based systems. So I'll just give you a quick feel for what it looks like to do this kind of work. And first we'll do ASCII-based messages, data that's encoded in plain text, ASCII. And then later we'll do a little bit of binary unpacking. So here are two examples of messages that transmit GPS coordinates and timestamp and identifiers and so on. So we'll just step through this quickly just to see the kind of things that you would look for when processing these messages and how you would extract the parts out. With these, they're pretty easy. The delimiters are obvious, and the documentation will tell you what to do. So let's step through it quickly. So it's very common for messages to have a header at the start and a terminator at the end to tell you what the start and end of messages is. And that's quite important because data comes in on streams. So you have to be able to buffer less or more and determine when the end is there so that you can chop it off and process it. Then the devices transmit identifiers, unique identifiers. And this is a big reason why TCP is preferred with a lot of devices. Because TCP has a very well-defined behavior regarding how the connection works, many devices will log on with their identifier, but they won't transmit it in subsequent messages because they don't have to. If a disconnection occurs, they will connect again with the identifier. And that saves some bytes on every subsequent message. So that's why TCP is very common. The timestamps are usually Unix timestamps, and they're almost always transmitted in UTC, which you begin to realize once you get a device that doesn't transmit in UTC and it transmits in the local time zone. And then you spend a great deal of time thinking about how do you convert that to UTC, given that you only have the GPS coordinates. That means you have to think where you are in the world and what time zone is it, and is there daylight saving? So we did not implement that device that transmitted in local time because you have to set up a whole other server just to be able to convert local time plus GPS coordinates into UTC time. And there you have the coordinates. The way of encoding these differs greatly from device to device. It just so happens that for these two that I've chosen here, they're similar, but they aren't always similar. Sometimes you have degrees, minutes, seconds separated. And sometimes they include signs. More often they include north and south, east and west. Okay, and I guess we're now getting to the point where it's like the lessons learned section of the talk. If you have to ever write this kind of code, these are things to watch out for. So time, datetime. Who enjoys working with datetime? So there's a trick to make datetimes work much better, and the trick is always specify time zone. Specify time zone every single time you create a datetime object, wherever the source comes from, specified in the constructor. That particular call there is really terrible, because what it does is it gives you the time in the UTC time zone as a datetime object, but without the time zone information in the object. So when you subtract that, what you get from that, from another time that is in the local time zone, you get obviously the time zone difference. There's not much you can do about that. And these kinds of bugs are actually pretty hard to figure out. You write your tests pass, you upload to your server, which is running in US East or something like that, and nothing works. Your time's all wrong. So always do that. When you create datetimes, always specify the time zone. So Python by default has the UTC time zone included, which you can get like that. This is Python 3. And if you need other time zones, there's a package called py.test, which offers all of them. And it's well developed and heavily updated. If there's one thing you take from this talk, specify time zones in all of your times. OK, so now we get to raw messages. The thing about raw messages is, yes, they are efficient. And I guess that's the main argument. And all of the device vendors support raw messages. But the problem is, it's really difficult to debug these things because what you get in the payload is this representation. And you can't easily determine what is in the message without actually writing the parser for the data. So if your job is to write the parser, you can't see what is supposed to be in the message in order to write the parser. So you have to follow the documentation to see what the sequence of bits and bytes is. And many devices can be configured to submit either binary data or ASCII data, and you have to do inspection. If you don't control the provisioning of the device, so you don't know ahead of time which one it's going to be, you can usually do some kind of inspection on the first few bytes, determine whether that's likely to be ASCII or binary, and then have a code path that deals with that. Documentation is quite spotty, and it's spotty in a frustrating way. This is an example of a minor frustration that you can clear up just by communicating with the vendor. So you can say, well, on this line where you said speed, you said knots, but then the example you said kilometers per hour, which one is it? Irritating, but you can deal with that quite easily. These are worse. So here you have an example of some binary data that gets uploaded, right? So when I wrote the tests for this, that message there at the top failed. It failed because its size was not the size that the header 2 pieces up said it was going to be. It said 60 bytes, but that was 59 bytes. It just so happened that in this specific case, a very similar message was transmitted later where it had 0, 1 at the end, and there was the missing byte. And there were 5 more below this. So you have to be a little bit of a detective sometimes to deal with these documentation problems. What you cannot do is just write the parser according to the documentation and assume that's going to work. That's not going to work. You have to write tests for everything to make sure that it works. And sometimes I write tests against the documentation and the examples that they give in the documentation, and the tests pass, and I set up the server. And occasionally a device that says it matches that protocol will submit data that fails. Exceptions get thrown on the server, and then I copy those payloads and I paste them into my tests and I add tests, and those tests fail. So it is actually quite difficult to make robust parsers for these device protocols. In principle, you can usually choose which vendors you want to work with, but if you're building a platform that is going to take everyone on, you don't really have that choice. I've done 15 protocols now for different vendors' devices, and all of them have been completely different. Not even similarities between any 2 of them, which is really quite interesting. Okay, so a couple of tools that you're going to lean on very heavily. The first is struct. The struct module in Python is amazing. You only realize that when you really have to do this kind of work. And this work that I've been doing in fleet management is really the first time that I've had to use struct heavily, and I've really begun to appreciate it. Just in case you haven't used it before, what struct does is it lets you chop up byte strings and assign them to different variables. So I'll give you a quick example of a heartbeat message that an 8-track device might send. This would be a heartbeat or a keep alive message that would notify you to keep the connection open. So first you have a keep alive header, and then you have 8 bytes for the device ID, and then you have a message counter. And if the particular device supports acknowledgements, you have to supply that same message counter back in the acknowledgement, and that's the way the device knows that that message was transmitted. If it does not receive the acknowledgement, it will transmit the same message again. So where struct comes in is it lets you unpack that sequence of bytes directly in one line. So there is a table in struct documentation that gives you a code for every different size of bytes. So H is short, 2 bytes. Q is 8 bytes and another 2 bytes. And you can unpack the data, and then you can get your 3 fields out on the back end. So that's really good. I use it a lot. There you can see we've unpacked our IMEI number and the response counter that we need to send back to the device. However, we can do better. What I found after using struct enough times is that there is a lot of boilerplate that has to go around how you use struct. What I've built is a tool for myself, and instead of showing the implementation of the tool, I'll show you how to use it, because you'll be able to build it yourself, definitely. This is a much easier way of doing the byte unpacking. You have one long string where you have name equals value, not value, but the byte size. So name equals format, one long string, and inside that function, you basically just split that by comma, and then you separate out the format strings from the headers. Then you do the actual unpack call that you would have done normally, and then when you get the results out, you assign them back to the others and you return a dict. It makes it much easier to access the values that you get out. So you can put a lot of the boilerplate that you normally would have to do around the unpack call, you can put inside that function. I would be quite surprised if there were other people who were heavily using struct who didn't have similar features like this. So yeah, there at the bottom. Tools like this make a huge difference. When you start doing repetitive kind of work like this, you have to build some extra tooling around what the standard library offers to make that easier. Okay, and this is the last slide. So Python has awesome support for number representation. It is really, really good. You can do bitwise, you can use bitwise operators to toggle bits and shift bits around and that kind of thing. But you can get a lot of mileage just out of the formatting support in Python itself. So here I've got a number, 21, and you can format it into hex, so that we get 15 out. And you can also specify the number directly, just beginning with 0x15. And that is actually a value of 21. Octal is supported there, although I haven't really used that very much. And you have binary support. So native built-in binary support. You can specify integers with the binary representation, and you can format integers as binary. It doesn't take too long to realize that you can start getting the exact width of bits that you want for a particular field, because struct gets you down to the byte level, but if you need to toggle bits inside a particular byte, which is quite common in the binary formats for the OBD devices, you really need to be able to toggle the bits directly or inspect them. So the binary formatting lets you easily log out which bits are set. So in your debug level logging, you can get very clear idea of which bits are set and then whether that matches up to the later data structures that you have set up to hold that information. So once you get into a string and you make sure the order is right, you can actually index into the string and check whether the thing is 0 or 1. So this is absolutely not as efficient as if you were to use bitwise operators, which is the normal way of doing this. But it reads very, very easily, and especially for testing and debugging, I've found these tricks to be enormously beneficial. And that's the end.
Questions? Got quite a bit of time for questions, but can you please make sure that all the questions are on the microphone? I think I'll hand it to people that want to ask questions.
Yes.
Oh, yeah. I'm going to run there.
So do you deal a lot with projections of data when you're working with this GPS data, or what are you actually doing with this in the end?
Right, that's a good question. I had intended to say that. So we're building a platform to let you register your vehicle's OBD device and have the data transmitted to us. And then we pass it, process it, and store it in a database and give you a user interface to see your travel time. For people who just want to see their travel time, that's fine. But for large companies who have significant fleets like Avis and other rental companies and long-haul trucking companies, they need to keep track of where their vehicles are moving 24/7. So we provide that service as well. So it's really, we're handling all of the processing of the information so that the end user doesn't have to do any of that stuff. They don't have to do hardware hacking, and they don't have to interpret the GPS stuff. They can get maps and PDF reports about travel times and distances and so on.
I've got a question. So would you also be, I've got a question as well. Would you also be able to, from the data, like if you see that like cars go here and you would see there is a congestion, like so every day.
Yes, absolutely.
Would you then be able to make recommendations to the driver like drive through here because cars pass faster here?
That is a good point. So that is something that one could do, but we don't do that. It's really just processing of the data. My employer has sold data before to the local municipal government in Auckland for exactly that reason, historical data to see where congestion points have occurred. And then that data has been used to inform decisions about where new roads should be built and so on. So the real-time information is interesting, but I find actually the data science is also interesting to look at historical congestion.
Given that you're dealing with OBD2 devices, are you actually pulling out any of the other information that they can supply, like the fuel levels, the acceleration, braking, these characteristics? Are you pulling any of those out as well, or are you just focusing on the GPS at this point?
We take everything we can get. Yeah. And that's frustrating, actually. So if you're building a common API that sits over everything, sometimes data doesn't always fit in the label that you give to it. Sometimes you have multiple fuel tanks in large vehicles, and if you only have one variable called fuel level, what do you do with the others? So it is kind of an arms race to figure out how to keep your API small and simple, but still gather all the information that is present in all the messages.
Yeah, I just wanted to ask, what database are you feeding all this stuff into at the back end?
Redis.
There you go. Cool. Working well?
So far, it's good. I'm curious to see what happens with scale, but it's pretty simple so far.
No worries.
So Redis is just for the device messages.
Yep.
I think we're using Google Data Store for all of the other stuff.
Okay.
But Redis is for the high throughput.
As a semi-related question, are you planning on exposing that sort of stuff as an API to your customers?
Yes.
Cool.
So do you run your own data center or do you run like somewhere in Amazon?
Yeah, Google.
Okay.
The Google's cloud platform.
Any more questions? Yep. Good question here. Can you...
If you wanted to do this yourself, do you have a device recommendation for which one would be the easiest to get started with?
That's not fair because Ryan has worked with me before on this. So he's trying to catch me out. For OBD devices, I think that the Boffin protocol that I implemented was probably one of the, not easiest, but the most clear, I think. It was fairly easy to see how they had structured their messaging and processing that. And there weren't weird and strange glitches in processing the messages. So that's a good choice. 8-track is also kind of okay. But my understanding is that the firmware is very variable in quality. The more expensive devices have good firmware, and the cheaper devices have really dodgy firmware. Like you'll get like crash notifications that aren't real, that kind of thing. You know, high G-force events. So I didn't talk about the hardware side of this, but the thing is, the hardware and the server-side software are not the only two things you have to care about. The firmware is actually where most of the problems happen. So, and if you're not doing that yourself, you really have to rest on whatever the vendor is giving you. And that's pretty hard because the firmware, my impression is that the firmware is really variable in quality. That's really, if you're going to be buying many of these devices, that's what you should focus on, is the quality of the firmware. Does the vendor do testing? How do they test their firmware? How rigorous is it? Those kinds of questions.
So you said you've got these 15 protocols. And I imagine when you receive a message, do you know at all which vendor or which firmware it's coming from, or do you sort of have to guess depending on the bytes that you get?
That's a very smart question. So we don't do that auto detection. We put each of the different protocols on a different port. So when you add your device to the system, you have to say which vendor it is. And then the URL that you are given back has the port that is associated with that vendor. So we separate out each of our server instances by protocol.
I think your colleague was first. So.
Have you guys given any feedback to any of the manufacturers about the total inconsistency of the device messages?
They don't care. At all.
Anyone working on any sort of open standard for that?
No. Not that I'm aware of. It may well be. And that's a good question, actually. So there is a project called trackcar.org, trackcar.org. It's a Java server that is an open source protocol implementation library, really. I think they have support for 800 different protocols. But the support is fairly shallow. So for many of those protocols, they just extract out the date and time and the lat long. But that's a good starting point to look at if you want to just jump in quickly. It is Java, though, so you may want to put on gloves. But yeah, that project is quite active. It has many contributors.
My question was similar. So obviously an open canonical standard for messaging for those 15 different vendors. Since you don't have one, do you implement some sort of SOA, like service-oriented architecture, after you receive all the messaging into a common canonical on your end before feeding it back?
That's exactly right.
Yeah.
So the Redis database that I was talking about, what we save in there is a standard format that we have ourselves. So another one. Yeah, so...
Have you thought about open sourcing that standard, that canonical standard you have?
It's tricky to do. The vendors themselves won't adopt it. But what we offer is a service that does the abstraction for you. So that's basically what the business is really offering. You know, it doesn't matter what device you have, you come to us, you just point it to our servers, and we will give you back data that's clear and consistent. Even if you have a heterogeneous mixture of devices, we can do that. To really push an open standard is just it's a thing that I don't think is going to be attractive for anyone to do. Unless the vendors themselves, like the hardware vendors themselves, come together and decide that they want to do that, which they won't do. The people who are leading in the field just they've got no interest in trying to share message protocols with other people. So that's quite tough. Teltonica's protocol was actually quite tricky to implement. They've got a recursive structure, a loose recursive structure where there are packets embedded in other packets, and you have to look at the byte header first and extract the rest, and then figure out what that is, and then inside that there are more. So that was quite interesting to write. So they would be a good example. Teltonica is huge. Especially in Europe, they're massive, and their protocol is probably one of the more arcane ones, and I think they've got zero interest to change because they're established.
We got any more questions? I think we can have one more. Okay, one last one. Thank you.
The best for last.
Just on the same topic again, is there any regulatory interest in forcing a standard protocol in terms of these are car devices, there's safety perhaps involved?
I don't know. All I know is that many of the protocol documents are full of spelling mistakes. The examples don't work. If there were an effort towards an open protocol, I think it would be good, but the amount of effort that is putting in now for vendors' own devices makes me, I want to be proven wrong, but I don't hold out a lot of hope that they're all going to decide to come together and meet and nail down that one protocol that they're all going to do. It's not that kind of world. The software world is like that, but the hardware world is just not like that. That's the impression I've got.
All right, thank you, Caleb. Can I have a big applause for Caleb?